Okay, we are going to talk about section 8.2, areas in the plane. So that's what we're working on here. You should have these notes, so hopefully you can find them. So how can we find, suppose we have two curves. We've talked about how to find the area between the curve and the x-axis. But what if you just have two different functions and you want to find the area of this shape here between the two curves? So what do? Well, one of the things we could do is we could split the area into several sections and we could use subtraction and figure it out. But there is an easier way. So rather, instead of doing that, when you have the two functions, there's a really easy way to find the area. So consider a very thin vertical strip here. The length of the strip is y1 minus y2. So the value, this y value from this function minus this y value from this function would tell you the length of that strip. Or since y1 is 2 minus x squared and y2 is negative x, you could write that as this expression here. That would be the length of that vertical strip. Since the width of the strip is a very small change in x, we're going to call that dx, a very small change in x. So we have the length of the strip, which is y1 minus y2. We have the width of the strip, which is dx, a very small change in x. And it's a rectangle, so how do you find the area of a rectangle? Well, you multiply the length times the width. So here's the length, here's the width, but that's just the one strip. There would be a whole bunch of strips, and we want to add them all up. And so we're going from -1, which that would be the x value at this point, and to 2, which would be the value over here at the end. So this is going from -1 to a +2. Now, what if you didn't know? How do you know that's a -1 and a +2? Well, you can find the points of intersection for these two graphs here. If you find the point of intersection and find out what that x value is and what this x value is, then you would have your limits for your integration. Okay, so again, it's this idea of this vertical strip. The length is just that you're subtracting the two functions. The width, in this case, is dx, but that's just the area of one strip, and then you're going to add them all up, which we're using our integral to show that. Then you could just do, you could go on and just do the antiderivative and plug in those values using the fundamental theorem of calculus, which I think they'll go on and do for you here. So just, you guys know how to do that, plugging in the values and coming up with your answer. So that would be the area in between the two curves. Notice the nice thing about that, we didn't have to worry about, is it above the x-axis, is it below the x-axis? We didn't have to worry about that when we were finding this area. So the formula to find the area between the curves is this. And all that is you are just subtracting the two functions and then integrating it from a to b, or wherever your limits are. And you won't really have to try and memorize it because it's kind of intuitive. You do a few problems and you got it. All right, so here's an example. So this top curve is the square root of x, and this is y equals x minus 2. And we want to find the area between them. Now the problem on this one is that it's not the square. If I were to draw in like a vertical line right here, because the x minus 2 would kind of drop down to here. So it's not just that this is the top and this is the bottom. So this one's a little tricky. I'm sure there's some words here that talk about that. So if we try vertical strips, we would have to do it in two parts. So you would have to split it right here. And from 0 to whatever this point is, you would just integrate the square root of x, because that would be 0. And then from whatever this point is to whatever this point is, you would subtract the two functions. So because you'd have to split it into two parts, because it's not like this is on top of this one for the entire time. So, so you'd have to do a little bit of extra work. So you'd go from 0 to 2. I guess we know the scale here, that you can see I guess this was from 0, 1, 2. So from 0 to 2, square root of x dx, and then you'd have to go from 2 to 4, where you have the square root of x because that's on the top, and x minus 2 is on the bottom. So, you could do that and do the antiderivative. You could still do that. But if instead you did a horizontal strip, and maybe you want to turn your head sideways, but if you notice with a horizontal strip that this y equals x minus 2 is on the top, and this y equals the square root of x is on the bottom the whole time, okay? So again, if you kind of turn your head sideways and you see that, we can do it with a horizontal strip, but notice that's a dy, which means my integral has to have y in it instead of x. So you have to do a little bit of work. If that's the case, you're going to have to solve for x in terms of y, because if you use a dx, then your function has to be in terms of x. If we use a dy, your function has to be in terms of y. So you would do a little bit of work here. You would have x equals y squared, and over on this one we would have x equals y plus 2. And then remember, the y plus 2 would be the larger, so it's going to go first. So we'd have the y plus 2 minus the y squared, and now we can use dy. Now, notice that they went from 0 to 2. They didn't go from 0 to 4. That's because if you're using y and dy, then these values here, you have to use the y values when you're setting up your integral. So it really all depends on, am I using vertical strips, which means it's dx, or am I using horizontal strips, which means the width of that is dy. So you have to decide that first so that you know how you should set up the function. Okay, so then that was the length of the strip. This was the width of the strip. And then you can do the antiderivative and solve that. All right, so here's the general strategy for area between curves. First thing you do is sketch the curve. So if you're not provided a sketch, you definitely want to sketch the curve so you can kind of see what you're working with. The second thing you do is decide on vertical or horizontal strips. So you're going to pick whichever is easier to write formulas for the length of the strip, or whichever will let you integrate fewer times. The fewer times you have to integrate, that's a little easier. So you want to decide on that. Then you write an expression for the area of the strip. If the width is dx, the length has to be in terms of x. If the width is dy, the length has to be in terms of y. That's important. Then you find the limits of integration. If you're using dx, the limits are x values. If you're using dy, the limits are y values. That's important. And then you integrate to find the area. I'm assuming this year on the AP Calculus test that, well, it's all, actually you can use your calculator. A lot of time, when on parts where you're not allowed to use your calculator, a lot of times they'll just say set up the integral, but you don't have to evaluate it. Setting up the integral is extremely important, and sometimes that's the hardest part. Okay. All right, so on this problem, and this is page 399 in your textbook, so I'm going to do a few problems. We want to find the area of the shaded region. So first thing you do is decide vertical or horizontal. So and so you can tell we're going to do a few, so you'll kind of see, but I'm going to do vertical strips so I can see that I can make a strip like that, and then I can see that the length of the strip is going to be y equals 1, so it's going to be 1 minus, and then this function here is cosine squared x. So that's the length. The width, since I'm dealing with, of the strip, is dx, which means my integral has to be going in the x direction. So I'm going to have an integral from 0 to pi, because that's where it goes from. And I will have 1 minus cosine squared x dx. That's my integral. So that's what I would do. Now, to evaluate this, because then we would need to evaluate that. So you could do finint on your calculator and do that. If you did this by hand, because you're going to have to do the antiderivative, what I would do, you know what, we're going to finint it. hold on a second. Okay, so if we do infinite, so number 4, we're going from 0 to pi, and we've got 1 minus, now this is tricky when you do cosine because we're going to do cosine x, and then we want to close that, and we square that, and that, it won't just square the x, it will, because it's going to close cosine before it squares, so that will do what we want it to do. And then we have dx, so we can type it in like that, and we get, our answer is 1.571 approximately. I'm guessing, because that's, I think, pi over 2. Had we done this with the antiderivative and did this by hand, we would have been able to come up with that in terms of pi. But as long as you are rounding to 3 decimal places, that is okay. Okay, so this next one, number 3, again, and actually, this is an interesting one because this one, you could actually do 2 different ways. Now, notice that I could do, because x equals y cubed, so I could do, I could set it up with vertical strips and do it in terms of dx, because this top curve is always, this from 0 to 1, it's always on top of the other one, so I could do that in one piece. Or notice I could also do this one with a horizontal strip, because this x equals y squared, again, turn your head sideways, it would be on top of the other one, and I could do it in one piece. It never switches, where one of them is, you know, above the other and then they switch. That never switches at all. It does after the 1, but that's, we're not interested in that. So you could do either way. However, look at the problem. You have x equals y cubed and you have x equals y squared. So you have them in terms of y. So if you, it's the problem's already set up to do a horizontal strip, because remember the horizontal strip, the thickness is dy. Okay, and I know sometimes you think, wait a minute, horizontal, shouldn't that be x and vertical y? But we're talking about the thickness of a horizontal strip, and so that would be dy. So because my function is in terms of y, and I'm going to do the dy instead of the dx, I'm going to do horizontal strips. So part of it is, what am I given? And you know how, you know, because I could have done this one either way, except I would have to do a little bit more math. So I'm going to have an integral. The length of my strip, the y squared is going to, it's farther, it's to the right, it's higher. Those values are going to produce higher x values. So we have y squared minus y cubed when I subtract, and then we're going to have dy, again, making sure everything matches, which remember then my integral also has to be about y, not about x, although here it wouldn't matter because I'm going from 0 to 1, so even if you messed up, you'd probably get it right. So here's my integral, and again, this one would be really easy to do by hand because you have y cubed over 3 minus y to the 4th over 4, and we're going from 0 to 1. So if you plug in a 1, you get 1/3 minus 1/4, and plug in a 0, you get 0. So we have 4/12 minus 3/12, which is 1/12, and actually that's our answer. We could also do with finance. So if we're going from 0 to 1, and I'm going to use an x because it doesn't matter. Your calculator doesn't know what, you know, which is which. So I'm just going to put in this. And since I'm typing it in as x, I need to put in a dx. And I get that value, which if I change to a fraction is 1/12. So you can kind of see how that works. All right. Next problem. Now this is one where it kind of does matter. I want to do this in as few steps as possible. So if I did this with vertical strips, notice that I'm going to have problems. My two functions, like this one, it's like the same function right here. So vertical strips are not going to really work on this one. I want to do horizontal strips because notice this function here, this one over here, 12y squared minus 12y cubed, is going to be the greater function, and the 2y squared minus 2y is going to be the lesser function. Another hint, because this is dy, look at my functions. They're given to me in terms of y. So this is going to be one where I'm going from, remember you have to have the y value. Well, let me just start with this. The greater value was this 12y squared minus 12y cubed. And then we're going to be subtracting 2y squared minus 2y. That's going to be dy. And this is going from 0 to 1 because you have to go in the y direction. So be careful that you don't go from, whatever this value is, which you'd have to find, to maybe 2 over here. You have to go in the y direction so we can go from 0 to 1. So this would be my function. You can clean that up a little bit, 0 to 1. So if I'm subtracting this, I'm going to have 12y squared minus 2y squared. I'm going to put the minus 12y cubed first. Then I'm going to have plus 10y squared, and then plus 2y dy. I changed this to plus and changed both those signs, so in case you look back and wonder what I was doing. So then you can finite this. You can do the antiderivative. I'm going to go ahead and just finite. Whoops. Okay. So we're going from 0 to 1, negative 12 x cubed plus 10 x squared plus 2x dx. So I get 4/3. Okay. Okay. So for this one, trying to find the shaded area, and I'm going to make use of the symmetry that I see, because I can see that if I go over the part that's on the left side of the y-axis, I can see it's exactly the same. So if I find the area of just part of it, of half of it, I can just double that area to get the area of the whole thing. So on this one, and again, this is one that you really could do vertical or horizontal strips because of the way that it's written. You could do either one, but because it's solved for x, it really makes more sense to do this, because then this would be dx, the thickness, and because these are in terms of x, I'm going to set it up that way. So the larger function is the 2x squared, so I'm going to have the integral of 2x squared minus, and then the smaller one is x to the 4th minus 2x squared. This is dx. And I'm integrating from 0 to 2. And then I'm going to double that because I have the same area on the other side. So when I do that, notice I'm going to have, well, this is going to change. So we end up with, let's see, negative x to the 4th plus, we have 2x squared plus 2x squared, so we have 4x squared dx. And then we can go ahead and, I know you can do these if you needed to, but we're going to go ahead and just finite it. Notice I could put the 2 out front and that won't matter. It will multiply for me. Negative x to the 4th plus 4x squared dx. And we get, let's see what this is, if it's 128/15. I prefer that because if otherwise I'm rounding. If I can do an exact value, I may as well. So so that's always a good idea. Okay, so on number 13, find the total shaded area. This one, there's no way you can do in one piece. You can't do it in one section. Now notice how the problem is set up. It's solved for x. So I prefer to do a vertical strip if possible, and I can, but notice that if I do a vertical strip on this side, the function that is on top is going to be this 2x cubed one, okay? And if I do a vertical strip over on this side of the y-axis, then notice it's switched. So I am going to have to do two integrals. I am doing it in terms of x, so let's take care of the one on the left first. So I'm going to do the integral from -2 to 0 and find the function that would be on the top, and that is 2x cubed minus x squared minus 5x minus the one that's on the bottom, which is -x squared plus 3x dx. That's my first integral. That just takes care of the left side. So it's the integral from -2 to 0, the top function being this cubic one, the bottom function being this one. So I'm subtracting that. Then I'm going to add to that the integral from 0 to 2. Sometimes you don't know exactly where these endpoints are. Sometimes you're not given the graph, and you have to figure that out. So you'll have to find the points. You can graph them on your calculator, find the points of intersection. So on this one now, the quadratic function is higher, so we have to switch that order. So this is what we'd be working on. So you could simplify that, you could finent that. I'll just tell you that the answer, if you want to verify this, is actually I don't think it's approximately equal. I think it's equal. At least my answer book says equal to 16. So you might want to verify that and let me know if it's different. So that is number 13. All right, so that is it for your this portion of that today. And then I'll have you try just a few problems and we'll get into more of the bulk of the assignment tomorrow.